Hello and welcome to our poster, Predicting Antibiotic Resistance in Mycobacterium Tuberculosis with Genomic Machine Learning. Now, tuberculosis infects more than 10 million people per year, and in its multi-drug resistant form, which is becoming more common globally, mortality is in excess of 40 to 80%. Part of the problem there is that diagnosis is slow. From patient presentation to definitive treatment, it can take up to 4 to 6 weeks because molecular assays for antibiotic resistance are very limited in their scope, and growing an organism of this nature is very laborious. So several members of our group formally looked at the potential of wide and deep neural networks to take in the whole genome sequences of tuberculosis, bioinformatically curate the mutants or genetic variants that might be of interest, feed them through the neural network, and predict resistance patterns for up to 10 different anti-tuberculosis drugs. And building upon the success of that model, we decided to take a leaf from the successes of convolutional neural networks in the imaging world to hypothesize that A, with such a neural network, we might not need to do so much data pre-processing, and B, be able to far more readily look at neighboring genetic regions as well as the genes themselves, and C, gain an insight into the black box of the neural network with saliency or attribution methods as a means of ascertaining which areas of the genetic sequence seem to be most pertinent for the neural network's predictions. In terms of the architecture, we invite you to take a closer look, but it was relatively straightforward. But I'll draw your attention to the input, which consists of about 10,000 different isolates or strains of tuberculosis, times 5 for the one hot encoding of the nucleotides, times 14,000 for the longest genetic locus, times 15 for the different genetic loci we looked at. In terms of the output, there were 13 nodes, each with a sigmoid function, generating a probability of resistance for each of those 13 different tuberculosis drugs. And if you look at the results, promisingly, the deep CNN was pretty much on par with the WDNN by the prediction AUC, ranging from 0.83 to 0.97. But in addition to what the WDNN could do, the convolutional neural network enabled us to check these predictions as a means of assessing its trustworthiness. An example is here with rifampicin. In the RPOB region, there's a very conspicuous saliency spike, and that happens to correspond with what's biologically recognized to confer rifampicin resistance. But in addition, we could generate hypotheses too with these saliency plots. So what I've circled here is part of the EMBA gene, where the neural network seems to have attributed these variants to be particularly helpful for making predictions. And this is more putative, for which there's growing evidence. So in essence, we have a promising diagnostic and research tool here where, by virtue of its greater interpretability, perhaps the CNN is more trustworthy, which is a very valuable trait in machine learning and in healthcare. It's more adaptable, it can hypothesize genomic variants, and it may lead to faster and more accurate diagnoses. Thank you for listening, and we welcome any questions and critiques. Anna and I will be here variably throughout the day. Thank you.